Okay, let's summarize what we got for this part of the chapter where we're saying that the wires are fixed, the wires are not moving. We showed that the EMF is the work per unit charge, and we showed that the work per unit charge in the case where the wires are not moving, they're fixed in space, is just equal to the loop integral of E, the electric field dotted into the elements of length. And that means that the magnetic force component doesn't contribute to the EMF. So this is something we did as a separate part in this part of the chapter, that the EMF for fixed wires is just integration of E dot ds. Then we showed Faraday Maxwell equation that tells you a relationship between the induced the electric field, the non-conservative electric field, and the rate at which the magnetic field is changing with time through the loop enclosed by the contour that you're integrating over. And so we did this in detail, and we showed how it works in principle. And we said that we're not going to solve problems in this form. We showed that it's possible to take the derivative with respect to time outside for this particular case when the contour is not changing shape or moving. So this is not true in general. You can't do this in general, but for this particular case where the wires are fixed, you can do that. And so we were able to then combine this part with this part and get this final result, that the EMF is minus the rate of change of magnetic flux, and the EMF is integration of E dot ds. So in some problems they might ask you for the EMF. Then you just get the magnetic flux and take the derivative with respect to time and multiply by -1, that'll give you the EMF. Some problems they'll ask for the electric field, so you can combine these two things to find the electric field like we did in one of the examples. So the prescription then to solve a typical problem is first to get the EMF, get the magnetic flux first, take the derivative with respect to time, then if you have more than one loop, multiply by the number of loops, and then get the magnitude of the EMF. Don't worry about any signs. So that's the magnitude of the EMF. Now, if you want to get the direction of the induced current, use Lenz's law. So this should be the way to solve most problems in this part of the chapter.